Hey guys, here we are getting ready to start a new chapter, chapter 4. Okay, and we're going to start it. It's Global Climates and Biomes, starting on page 86 to 87. First, we're going to start with our case study, our opening story that always kind of starts us off right at the beginning of the chapter. This one is about Kenyan climates. Kenya is a country in Africa, of course, and it kind of is really a good example of how climates can affect different parts of the same country or the same continent or the same ocean in drastically different ways. All right, so we're going to go back to about 2003. And during that year, they had really, really crazy climate. And we'll talk about the reasons that climate occurs here in just a second. But what was happening is that in West Kenya, they had a bunch of flooding. They had 70 people die. They had mudslides. And then they had a disruption of the water treatment plant that was cleaning all the water. Right? And they didn't really know why it was happening. They knew that usually their climate had kind of this increase in rain and then decrease in rain every year, but this one, the rains just never went away. Right? And then on a different side of the country in northeast Kenya, they were having the opposite problem. They were having major drought. They had 50 or more deaths. They had crops and meat animals died. So this guy down here is a Kenyan man walks through a cornfield that has been killed by drought. Because in places like Kenya that aren't super developed, they don't have like the big sprinkler systems like we do here in America, because they cost a lot of money and water costs a lot of money, especially in a more desert area. People would have to walk 2 hours just to get water, fill up as much as they could carry, and then carry it back home. And then there were 2.5 million people that were at risk to starve to death or to die of different drought-related diseases. All right, so scientists are still kind of studying this. I like all these questions up here. It says, what caused Western Kenya to suffer unusually heavy rains and floods, while northeastern Kenya was hit by devastating drought? In other words, why didn't rainfall in Kenya occur in a predictable pattern during this period? All right, now we're talking about El Nino. Right now we're in an El Nino year, which is why our weather has been so crazy. We'll talk about that a little bit later on. But what I want us to understand from this is that many, 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 many factors drive climate. And as humans are doing what humans do and burning our fossil fuels and not really having much considerations for the planet and cutting down trees to build animal farms and things like that, we could be seeing more and more just drastic changes like they did in Kenya. All right, so first, we're going to talk about the difference between weather and climate, because a lot of times people kind of lump these two words together, but there are very, very distinct differences. So weather is going to be our short-term local state of the atmosphere. Remember, ATM is atmosphere. And weather is going to be measured in anywhere between seconds and days. So usually you'll have like your 10-day forecast or your 5-day forecast, and that's a weather prediction. All right. Then we have climate over here, and climate is the average weather in an area over a long time. Okay, so this is measured in decades, sometimes centuries. For example, in Colorado Springs, we know that we have usually pretty hot summers with thunderstorms, and then cold winters with snow. And that has been proven year and year and year and year over and over and over again. So we know that our Colorado Springs climate, when people ask like if they're going to move here or if a company's going to move their factories over here, they have an accurate prediction of what the climate is going to be like, and it's more of a predictable thing. Weather is not as predictable, as we know, because the weatherman is often wrong. All right, so we have a couple general observations about climate. We know that at the poles there's a lower temperature than the equator, of course, and an increase in elevation means a decrease in temperature, and that temperature and precipitation determine which organisms can survive in each region. All right, so we know that as latitude increases, temperature decreases. As altitude or elevation increases, temperature decreases. And then temperature and precipitation together determine which organisms can survive in each region. We talked about this a little bit when we were doing our watershed activity, and you're going to learn a lot more about this when we talk about biomes. But for example, like a cactus could not survive in the North Pole, polar bear could not survive at the equator. Okay. Now we have all of these layers of the atmosphere, and there's a really nice visual right here. This figure 4.1, layers of the Earth's atmosphere, it kind of gives you a nice progression, and this red line is the temperature graph. It goes from negative 100 degrees Celsius to 1,750 degrees Celsius. All right, and then on this axis here is the altitude in kilometers. So 0 kilometers would be right at Earth's surface, right where your feet hit the ground, and then 600 kilometers would be the end of our atmosphere. Okay, so we're going to go from top to bottom here. Okay, so we are going to start at the exosphere up here, and then we're going to go down to the troposphere, which is down here. I drew a little person because that's where the people are. All right, so the exosphere, that's going to be our farthest from Earth. It's going to have the lowest amount of pressure. We could not travel out there without some sort of heavy protection because the temperature is so high and the atmospheric pressure is so low. All right, and then we have the thermosphere. Thermo should remind you of thermometer or temperature. And as you can see in the thermosphere, the temperature is rising significantly. Okay. The thermosphere's job is to block UV and X-rays from the sun, because the sun's constantly putting out radiation in the full electromagnetic spectrum. So the thermosphere is going to block the UV and the X-rays. It's full of these charged molecules. Okay, they're charged with solar energy, and sometimes they can end up reacting. So the solar radiation reacting with the gases in the thermosphere actually are what create this aurora borealis that you've probably seen. So these northern lights or southern lights. All right, so it also is where the magnetic field is in the thermosphere, and it's the strongest at the poles, which is why your compass can point north or south. Okay, and then the aurora borealis is in the northern hemisphere, and then the aurora australis is in the southern hemisphere. I find that easy to remember because australis sounds kind of like Australia, and Australia is in the southern hemisphere, so that kind of makes it easy for me to remember. All right, the mesosphere is in the middle. Meso means middle, so that should help you remember that. The stratosphere is pretty close to us here. It has a pretty low density and a very high temperature due to the ozone. Okay, so stratosphere is where the ozone layer lives. Okay, so O3 is ozone, and it absorbs UVB and UVC rays. Okay, and that's critical for life being able to survive on Earth. All right, whenever we have our skin or plants be radiated by UVB or UVC, that's going to cause things like cancer and melanoma and things like that. So the ozone layer is absolutely important to survival of life on Earth. Without it, we would not be here. Okay, so over here I put the UV radiation being absorbed by the stratosphere that's why it increases in temperature. So it gets lower and lower and lower, and then higher, lower, and then high. All right, and then we have our troposphere, which is closest to us. It's the densest layer. We have things like clouds. okay, and organisms, lots of organisms that live here. In these upper layers, really all it is different gases, so it's not going to be very dense. We have mostly nitrogen. Nitrogen is the most abundant gas, then oxygen, then water. All right, and water is actually a greenhouse gas, and we'll talk about those a little bit later on this year. Temperature generally decreases with altitude, okay, which is why when you go up in your airplane, it usually gets pretty cold. And if we didn't have like insulated planes and stuff like that, they wouldn't be able to fly at such a high altitude. In the troposphere, there's a lot of circulation and mixing of gases. We know the mixing of gases in the circulation as wind. We know it as wind. There's not a whole lot of that happening up here, because as soon as you get like past the exosphere, it's going to be a vacuum anyway. So what you want to try to do with this is create some sort of like mnemonic device, like a word that starts with each of these letters to kind of help you remember which order they go. Okay, because sometimes it's easy to get the stratosphere and troposphere mixed up. Sometimes it's easy to get thermosphere and mesosphere mixed up. So what you want to do is try to make a sentence and have each word in the sentence start with the letter of the atmospheric layer name. Okay? All right, now we have, as you probably already know, we have unequal heating of the Earth. We know that there is much more radiation that comes in to the equator, which is why we have tropical places like Florida and the Sahara Desert. And then we also have places like the North Pole and the South Pole that actually never melt completely. Okay, so there's 3 different causes of this unequal heating, all of them very important. So the first cause is the angle that the sun rays hit the earth. Okay, and I really like this figure right here, so I kind of recreated it on my sticky note. So I know that if the sun's rays is coming in towards the North Pole, it's going to hit the earth and deflect off, okay, or reflect off, and it's going to be at an oblique angle, which I hope we all know is greater than 90 degrees. So that's going to end up reflecting more because it just gets reflected off the top and then it's gone and it's not holding on anything. It's not keeping any energy in. So we know that this oblique angle leads to less energy being absorbed by the land and stuff around this area. Okay, land and water. Now at the equator, we have a perpendicular angle, which means that there's going to be much more that's going to be absorbed. It's not going to be just deflected off right away. It's going to stick around for longer. So there's going to be more radiation at places like the equator. Okay? So it says, at high latitude, sunlight must pass through more atmosphere and thus loses more of its energy than in the tropics. At high latitudes, a given amount of solar energy is spread over a large surface area than the equator. Okay, so that's cause number 2. It says surface area the sun's rays cover. Okay, so we could recreate this with flashlight. We could pretend that the sun's rays are a flashlight, and if you shine a flashlight, you're going to have this little perfect circle that's going to be really, really bright. But if you having at that oblique angle again, and you shine your flashlight at an oblique angle, you can actually try this at home if you want. It's going to create a larger but less bright circle. So that means that less radiation is going to be, it's not going to be as concentrated. So at the equator, the Earth's radiation is the sun's radiation is pretty concentrated. At the poles, it's going to be much less. Okay? The last cause is going to be that some areas reflect more or less solar energy, and that is called albedo, which is our last figure down here. This is our albedo chart. All right, so the albedo is the percent of incoming sunlight that is reflected by a surface. Okay, so all of these are given to you in percentages. So this is how much is being reflected. All right, so in water, 10 to 60% is being reflected off of water depending upon the sun's angle, which, like we talked about up here, is very important in multiple processes that make the earth take in energy at an unequal rate. Okay. I like to think of it like cars or shirts. So white surfaces, white cars, white shirts, they have a higher albedo, which means that they have a lower temperature. All right, so fresh snow is a good example of that. It has 80 to 95% albedo, which 80 to 95% is being reflected, so it's going to stay cool. It's not going to melt as fast. Okay, versus black surfaces are going to have a lower albedo and a higher temperature. So if we think of the darkest thing on here, it says asphalt. Okay, it says asphalt has only 5 to 10% albedo. So only 5 to 10% is being reflected. The rest is being absorbed, which is why if you try to like walk on the road on a hot day, it's going to be really hot on your feet. Or if you get in your black car in the middle of summer, it's going to be much hotter than if you had a white car because it's absorbing more and reflecting less. Okay, so white is reflecting more, which is why it stays cold. Black is absorbing more, which is why it stays hot. All right, and that's all we have for today. I will see you guys in class so that we can practice some of these concepts.